Okay, we mentioned earlier that water is amphoteric, and that word amphoteric means it can act as an acid or as a base. And what's kind of funny is even in pure water, it will do this. It will act as an acid and a base with itself. And you might say, well, why would it want to do that? Well, maybe because it can. It doesn't do it a lot, though. So if you have one water molecule and another water molecule, one can act as an acid and donate its proton to the other water molecule, which acts as a base. And the result is we get hydronium ions and hydroxide ions. Now this is a double-headed arrow here. This is an equilibrium. And this happens only to a very, very small extent. That's why pure water does not conduct electricity. It does have some ions in it, but very, very few. It's called self-ionization. Water is ionizing itself. Let's go back to that equation for a minute. If we start with pure water, the concentration of hydronium ions and hydroxide ions that's produced has to be equal, right? Because we take two water molecules and we get one of these and one of those. You couldn't get one hydronium and three hydroxides from this reaction. It's like buying shoes, they come in pairs. You're going to have an equal number of right and left shoes, no matter how many pairs you buy, right? So these pair up, and we're going to get one hydronium and one hydroxide from each of them. So for pure water at 25 degrees Celsius, those concentrations are equal, and they are 1 times 10 to the minus 7 moles per liter. So that's 0.000001 moles out of 1 liter of water. That's a very small concentration. I'm just going to go back to this equation again. This is one of the reasons why I like having already covered chapter 15. Your book hasn't gotten to 15 yet in equilibrium constants, and so it can't do it for you here, but I'm going to. If we look at this equation here and wrote an equilibrium expression for it, right, we would say that K at, choose a writing tool. We'd say that the equilibrium constant equals the concentration of each product, right, times its, raised to its coefficient. All the coefficients are 1 here. So that would be hydronium ion to the first power times hydroxide ion to the first power. And then we divide by the concentration of the reactants. But these are liquids. Liquids and solids can't change their concentrations, and so they don't come into the equation. So the equilibrium expression for this self-ionization of water would be the equilibrium constant is equal to the concentration of each of these times each other. Well, because this is kind of a special situation, instead of just calling this KEQ, we call this KW for water. It's the self-ionization constant for water. So KW equals the hydronium ion concentration times the hydroxide ion concentration. Well, each of those concentrations is 1 times 10 to the minus 7. You multiply them together, you get 1 times 10 to the minus 14. Is that a big number or a small number? Small number. So does this favor the products or the reactants? I know, chapter 15 was a while ago. If the equilibrium constant is larger than 1, it's going to favor the products. If it's less than 1, it favors the reactants. So this strongly favors the reactants. So we've got these concentrations, each are 10 to the minus 7, and in a neutral solution, we have the concentrations of each of these being the same. Any questions? Yes?
So water does have ions in it, just not enough to conduct electricity.
Right. Water does contain ions, but not enough to conduct electricity. So, neutral solution, that's where we have these being equal. If we add an acid to the water, we're going to increase the hydronium ion concentration. The hydronium ion concentration is going to be larger than 1 times 10 to the minus 7. And then what does that do to the equilibrium? Remember Le Chatelier's principle? So let's write it this way. 2 water molecules in equilibrium with hydronium and hydroxide. So we start out with pure water. We've got 10 to the minus 7 and 10 to the minus 7. And we put some acid in and we increase this concentration. What does the equilibrium do? It shifts away to undo what we did to it, right? If the reaction shifts to the left, sorry, this L is bothering me. If the reaction shifts to the left, then some of the hydronium ion that we added is going to react with the hydroxide ion that was already present, right? So the hydroxide ion concentration will be lower than it was before we messed with it. Because this times this still has to equal the equilibrium constant. So the hydroxide ion concentration will be less than 10 to the minus 7. The hydronium ion will be more. If we have a basic solution, if we take this neutral pure water and we add a bunch of hydroxide to it, what's going to happen to the equilibrium? It's going to shift the same way. It's going to shift to the left to undo the adding of the hydroxide. So that'll take away some of what we added, but it will also reduce the hydronium ion concentration. So in a basic solution, we have hydronium ion being less than 10 to the minus 7 and hydroxide being more. In all aqueous solutions, those two concentrations multiplied together have to equal 10 to the minus 14. Any questions? So the hydronium ion and hydroxide ion concentration are interdependent. They depend on each other. Here in the middle, with pure water, we have those concentrations being equal. If we increase the concentration of the hydronium, then the concentration of the hydroxide has to decrease correspondingly. If we decrease the hydronium ion, then the hydroxide ion increases. So this would be a basic situation, and this would be an acidic situation. Okay, so this problem asks us to calculate the hydronium ion concentration in each solution and decide if the solution is acidic, basic, or neutral. So they're giving us hydroxide ion concentration, and they're asking us what the hydronium ion concentration is. We're using the equilibrium expression to do this problem. So Kw equals 1.0 times 10 to the minus 14. And that equals the hydronium ion concentration times the hydroxide ion concentration. So if we know the hydroxide ion concentration, we can calculate the other one. If you rearrange this equation, you divide both sides by hydroxide ion, and you get the hydronium ion is equal to 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration. So that's the general equation. And so for this first one, it'll be 1.0 times 10 to the minus 14 divided by 1.5 times 10 to the minus 2. So get out your calculation. Get out your calculator. 1 EE minus 14 divided by 1.5 EE minus 2. And this would have 2 sig figs. So I'm going to report the answer as 6.7 times 10 to the minus 13. What should the unit be on this concentration? So these equilibrium constants were arbitrarily unitless. And these things in the brackets, just because we decided, they're always in units of moles per liter. So even though the units don't look like they would be working out here, this would be capital M. So 6.7 times 10 to the minus 13 molar hydronium ion concentration. So is this acidic, basic, or neutral? Does it have more hydronium than pure water or less? It has less. Here we have a negative exponent. Those negatives, you just have to stop and think about them. The bigger the negative exponent, the smaller the number. So this is a very small concentration, and this concentration is larger than 10 to the minus 7. So more acid means that this is an acidic solution. Any questions? So that one's acidic. For the second one, the calculation is the same with a different number. If you're really on top of things, you might realize, oh, we don't actually have to do this calculation, but we're just going to do it anyway. If I do the math, I come up with 1.0 times 10 to the minus 7, and then I put molarity on there because I know that's what the unit's supposed to be. Acidic, basic, or neutral? Neutral. These are the same. The concentrations of hydroxide and hydronium are the same, and that's what you have in a neutral solution. So for this last one, the hydronium ion concentration is Kw, which is 1.0 times 10 to the minus 14, divided by the hydroxide ion concentration. Here it's 8.2 times 10 to the minus 10. So 1 EE minus 14 divided by 8.2 EE negative 10. (1.2 times 10 to the minus 5). Anybody else get that number? Acidic, basic, or neutral? Basic. No. What? Okay. Let's go back to the first one. The first one isn't acidic. I'm having a brain fart. The hydroxide ion concentration is bigger than the hydronium ion concentration. That means that one's basic. And so this one is acidic. Yes? Mm-hmm.
Then it would switch, right? Because in that case, if the number was larger, it would be acidic.
Yeah, if this was the hydronium ion concentration and this was the hydroxide ion concentration, then it would be acidic. Yeah. So that was really bad on my part, messing those up. Everybody makes mistakes. Any questions? I think I've already made more than my quota for today.